Imagine a massive star located on the distant outskirts of our Milky Way galaxy, blowing a powerful cosmic blowtorch that's visible from millions of miles away. This isn't just a fantasy. It's a real phenomenon that's been captured in stunning detail by the James Webb Space Telescope's near-infrared camera. The star in question is shooting out twin jets that stretch an astonishing 8 light-years long, forming a nebulous structure known as Sharpless 2-284, or SH 2-284 for short. But here's where it gets really interesting. These jets are expanding at a rate of hundreds of thousands of miles per hour, and their existence is proof of the process by which the most massive stars in the universe form. As Jonathan Tan of the University of Virginia and Chalmers University of Technology in Gothenburg notes, once we found a massive star launching these jets, we realized we could use the Webb observations to test theories of massive star formation. But what exactly are these stellar jets, and how do they form? Essentially, they're fueled by material, mostly hydrogen gas, that's falling onto a growing star. This material bunches up into a disk around the young protostar, and some of it is absorbed by the star, increasing its mass. However, if too much material accumulates in the disk, some of the excess is flung away by tightly wound magnetic fields that beam the material out in 2 jets along the young star's axis. Now, you might be wondering how this process differs for low-mass stars versus more massive ones. Well, low-mass stars tend to form in a relatively orderly fashion, but the formation of more massive stars is thought to be more chaotic. One theory suggests that the accretion of infalling gas is more turbulent, resulting in the star and its accretion disk wobbling about, and the jets moving, twisting, and spraying across a larger area. However, the JWST image of SH 2-284 shows no evidence of the jets having moved, with them being straight and pointing almost 180 degrees opposite one another. This implies that the star's formation has not been chaotic at all. But here's the thing. Models of star formation suggest that the size of the jets scales with the size of the star producing them. And according to these models, the star in question is about 10 times the mass of the Sun and is still growing, having powered this outflow. The fact that these jets are so energetic, straight, and narrowly collimated can help astronomers better understand the environment in which stars like this form, as well as the intrinsic properties of such stars. As Yu Cheng of the National Astronomical Observatory of Japan, who led the JWST observations, notes, "We didn't really know there was a massive star with this kind of superjet out there before the observation." And this is the part that's really significant. The discovery of this star and its jets is shedding light on the formation mechanism of massive stars in low metallicity environments. You see, the star is located 15,000 light-years from Earth on the very outskirts of the Milky Way's spiral disk, where the abundance of elements heavier than hydrogen and helium is low. This is because such elements are formed within stars, and star formation on the outskirts of the galaxy just hasn't been vigorous enough to produce many of these elements. But what does this mean for our understanding of the early universe? Well, the conditions in this region of the galaxy mimic those found in the early universe, making this star a kind of laboratory for studying what was going on in earlier cosmic history. And if we look at the history of SH 2-284, we can see that the tips of the jets are the oldest part, with the young star's life chronicled in the long extent of the jets. As Tan explains, originally the material in the tips was close to the star, but over 100,000 years, the tips were propagating out, and then the stuff behind is a younger outflow. Now, the growing star itself is not visible directly, but the JWST is able to pick out the structure of SH 2-284 with filaments, knots, bow shocks, and linear chains of clumpy material, all arising out of the jet's interactions with the surrounding interstellar medium. But here's the thing. As powerful as these jets and the nebulosity they produce are, they're only transitory. Eventually, the star will emerge from its cocoon, fully grown with possibly tens of times the mass of our Sun. Its lifetime will be limited to a few million years, and then it will explode, creating a whole new nebula, one of star death, not birth. But its legacy will be to enrich space with the metals that it forged, and the cycle of stars will continue. So what do you think? Are these massive stars and their jets the key to understanding the formation of our universe? Or is there more to the story? Let us know in the comments. The observations of H2284 were reported in the Astrophysical Journal, and we'd love to hear your thoughts on this discovery.